Hi everybody, my name is Jeremy Krug, and the 2022 AP Chemistry free response questions have been released, and so I'd like to take a little time to work through these with you. And if you'd like to take a look at these going forward, as I'll be releasing these over the next several days, go ahead and subscribe to my channel so you won't miss any of these explanations. And a little disclaimer, I am not the College Board, I'm not AP. I am just an AP Chemistry teacher who has successfully taught AP Chemistry to hundreds of students over the last 22 years, so I will do my best. And so we'll jump right into question number one. So question number one was a stoichiometry question, pretty straight up, simple stoichiometry, where we take 0.300 grams of methyl salicylate, and they give us the formula for that, C8H8O3. And the question is to calculate the maximum mass in grams of salicylic acid. So way down here at the end, we're trying to convert to grams of HC7H5O3. So this is just a simple three-step stoichiometric process here. So step one is convert to moles, so 1 mole on top and grams on bottom. They were nice enough to actually tell us the molar mass, 152.15. Grams are canceled. Then the next step is the mole ratio. And so we have to put methyl salicylate on the bottom, C8H8O3, and salicylic acid on top, HC7H5O3. Now there is no balanced equation, but the problem comes right out and tells us that this is a 1-to-1 mole ratio, 1 mole for each of those. So in this case, we don't actually need the balanced equation. Very unusual for that, but they actually come out and tell us that. The third step is convert back to grams. So once again, 1 mole on the bottom, and this time it tells us that it is 131.12 or 138.12 grams in a mole of salicylic acid. So you can cancel moles top and bottom, do the math here, and I'm getting an answer of about 0.272 grams of salicylic acid. So that is part A. As we move on to part B, we have an experiment here that's going on with these, and we're trying to purify the crystals, and we're going to filter them, rinse them with distilled water, and dry them. And we have some data based upon this. It tells us that the experiment from the student here got an 87% yield of dry salicylic acid. And so the student says, well, perhaps some of the salicylic acid crystals dissolved in the distilled water during the rinsing step. And is this consistent with the percent yield? I would say yes. And maybe someone will prove me wrong later on, but based upon what we see in the table here, it looks like salicylic acid is moderately soluble in water. So I believe that tells us, 2.2 grams per liter, it'll dissolve a little bit. And since we only had about 0.2 grams or something like that that were produced, it is very conceivable that a small amount of the acid was washed away during that rinsing process. And so I'm going to say yes on this. And based upon the solubility, and that, not all of it, but that some of it, a small amount, 13%, was washed away, because you got, the rest was still there. So on to part C. This one is a thermochemistry question. We're taking some of this salicylic acid at 25 degrees Celsius, and we're raising it to 159 degrees Celsius, but we're not just raising it to that temperature, we're also melting the crystals completely. So the question is, how much heat does this require? Well, there are a couple things we have to do. The first thing is raise it to 159 degrees Celsius. So that's where Q equals MC delta T comes in. So we're solving for the amount of heat. The mass is 0.105 grams. The specific heat capacity of this from the table that we got on the last slide, if we take a look at that, is right here. It's 1.17 joules per gram degree Celsius. And then the delta T from 25 degrees Celsius to 159 degrees Celsius, if my math is right, that's about 130 34 degrees Celsius that we're actually raising that temperature by. So when we multiply these across, it looks like it's going to take 16.5 joules in order to raise the temperature to that level. Now, that's not all though, because we also have to melt the crystals completely. That's a separate process. That's where the heat of fusion comes in. Okay? So the heat of fusion, that's melting it. That's how much energy it takes to melt this stuff. So it's 27.1 kilojoules per mole to melt it. So that's a separate Q. So the Q of the actual fusion or the melting process, it says we have 0.105 grams, and the heat of fusion is given to us in moles, so we have to convert this to moles first. So I have to put 1 mole on top, and the problem says that it is 138.12 grams in a mole of that, so we cancel grams. And now we can use the heat of fusion. I'm going to put moles on the bottom. I'm going to put kilojoules on top. And the heat of fusion is about 27.1 kilojoules per mole. And so moles are out. And now I am in the kilojoules, and I'd like to be in joules so I can have the same unit there. So I'll just put the kilojoules on bottom, joules on top. It's 1,000. And so that's out. And so when I do my math here, if I did this right, I believe it's about 20.6 joules for the fusion, for the actual melting process. So now the question is, what's the total quantity of heat? So I actually have to add these two together. So the total Q here, the total heat, is just adding those together, the 16.5 joules plus 20.6 joules. And so when I add those together, I get about 37.1 joules. And so that's my answer for part C. We can go on to part D now, and we have a structural problem here. We have the actual structures of these two molecules, and we have a statement here that all three of these have LDF, London dispersion forces, dipole-dipole forces, and hydrogen bonds. However, why is the melting point of salicylic acid so much higher? Well, that's like 168 degrees higher. Why is that the case? Well, as I look at these, I see that there are two OH bonds on the salicylic acid. We have a hydroxyl group right there, and one right over here, or the OH, the OH I should say, and there's only one over here. So since the salicylic acid has two of those OH bonds compared to only one OH bond over on the methyl salicylate, that tells me that the salicylic acid has two sites where hydrogen bonding can occur. And so as a result, I would say that the hydrogen bonding in salicylic acid would be much stronger than the hydrogen bonding in methyl salicylate. And because the hydrogen bonding is stronger in the salicylic acid, well, that correlates, or that causes, a higher melting point. You want to say that as well. I'm writing very quickly here so that this video doesn't last 30 minutes. So anyway, that's the idea there. You have more OHs, and so you have more stronger hydrogen bonding. Now, part E, we have a nice little titration graph, a titration curve, excuse me. And so the student titrates 20 mils of the salicylic acid at 0.01 molar with 0.02 molar sodium hydroxide using a probe to monitor the pH of the solution. So here's our titration curve. And part E says, using the information in the graph, estimate the pKa of the salicylic acid. Well, one thing that you have to know for this is that the pH at the halfway point of a titration is equal to the pKa of the weak acid that's being used. So the equivalence point, as you can see here, is reached at 10 10 milliliters, excuse me. So it's been a long day. So that means that the halfway point is right here at 5 milliliters. So it's right there. So if we just move up here, we can get right there. And it looks like the pH at that point is 3 or just maybe a touch above 3. And so I'm going to say about 3.1 seems to be my halfway point pH. So that's the pKa. Okay, so that's the key thing to know here. pH at the halfway point equals the pKa. Now, part F says when the pH of the titration mixture is 4, which predominates? Is it the salicylic acid or is it the salicylate, the conjugate base in the flask? And justify. Well, let's take a look at what's going on at pH 4. So here's pH 4 right here. And so as you'll notice, at pH 4, we are more than halfway. So since we are more than halfway, okay, well that indicates to me that we've added more than half of the base that's going to be added. So more of the base, which is the hydroxide, predominates, more sodium hydroxide. Now, as a result, you know, on the this is the halfway point, and so on the left side of that, it's the acid form that predominates. On the right side, or as you go closer to the equivalence point, it's the base form that predominates. So as a result, it's the conjugate base that predominates. It is that ion right there, and the justification is that you're more than halfway to the equivalence point. And so you have a lot of hydroxide that has already reacted with the salicylic acid, and so you have a whole lot more of that stuff right there. Okay, so that's your answer for F. On part G, this was an interesting question. It gave us the Ka for a different acid, benzoic acid. What is the pKa for benzoic acid? And I don't know if I've seen a question like this on the AP exam before. All you have to do is take negative log of Ka. That's to me, or at least in my opinion, that's a very simple question. But you know, more points the better. So negative log of 6.3 times 10 to the negative fifth. You calculate that. Looks like the pKa is 4.20. 4.20 is your pKa. Okay. So now for H, we have a slightly different question. It says, this time we're kind of doing a similar titration as in the last titration curve, except instead of salicylic acid, we're doing a benzoic acid. It says sketch the titration curve, and it says we start out at 3.11. So there are a few points that you need to have on here. You need to have 3.11 as your starting point, so that's just a touch above the 3, so somewhere around there. And I know the computer does not like it when I try to make dots on here, but I'll do my best. And then we also have to keep in mind this point right here, that at the halfway point, the pH is 4.20. The pH equals pKa at the halfway point. The equivalence point is still 10 milliliters. So 5 mils, you want to draw at 4.20. So that's right around here. Okay, so draw that point right in that. And so once again, we are going to have a titration curve that kind of mirrors what the other one is, except it's a little bit higher. And, you know, at the halfway point, it's 4.20. Then you keep going, and then once it hits that 10, it's going to shoot up, just like the other one did, just like crazy. And then once it gets a little above there, it's going to level out and kind of level out there. So that's your titration curve for H. And so if you are trying to count up points, once again, there are about 10 points that can be calculated here. If I were calculating the points here, and once again, this is just an unofficial count, I would take a guess that on part A, that they would probably give, change colors here, they probably would give 2 points for this. I'm going to say maybe 1 point for calculating the moles of the methyl salicylate correctly and 1 mole for that. So 2 points for part A. I'm going to say part B would be 1 point. I'm going to say part C would probably be 2 points. I'm going to guess 1 point for that, 1 point for the fusion part, and then a third, and then possibly, I'm not sure, possibly a point in there for adding it correctly. I don't think that they'd give more than 2 points for that one. Part D, I think, is a point. Part E should be a point. Part F should be a point. Part G should be a point. And I think H would be a point, and they're probably looking for that point right there, the halfway point. So anyway, that is the solution. At least that's my solution for question 1. I hope you enjoyed this. I hope you got them all right or got a lot of points right. If you learned something or at least appreciated the explanation, please give me a thumbs up and subscribe to my channel. I'll be putting the rest of these up as the days go on, and hope to see you again on my channel where we can learn some more chemistry together.